Millions of visitors travel to Yellowstone National Park every year to walk among the hot springs, fumaroles, and geysers. But the geothermal heat that makes this landscape so extraordinary is powered by something hidden deep underground. Old Faithful is an iconic tourist attraction. It is also a mechanical symptom of a highly active geological system. This diagram illustrates what lies below the park: a magma chamber 90 kilometers long, 30 wide, and 15 deep. It contains up to 20,000 cubic kilometers of molten rock. As this magma expands and contracts, Yellowstone's surface physically rises and falls every year. The tourists walking along those wooden boardwalks are standing on top of a breathing, active geological threat. We know exactly what this system is capable of because it has erupted 3 times in the past 2 million years. The most recent eruption occurred roughly 640,000 years ago, ejecting approximately 1,000 cubic kilometers of material into the atmosphere. It blanketed most of the western United States in a thick layer of volcanic ash. This geographic map isolates the physical scar left behind by that blast, a collapse crater, or caldera, measuring roughly 72 kilometers long and 55 kilometers wide. The modern infrastructure of Yellowstone sits inside the remnant of that eruption. Ejecting more than 1,000 cubic kilometers of material is the strict scientific threshold required to classify a system as a supervolcano. There are only about 20 known sites of this scale on Earth. The historical interval between Yellowstone's second and third eruptions was roughly 660,000 years. The last one was 640,000 years ago. While geology isn't a perfect clock, the statistics suggest we are inside an active window for an event large enough to alter the global climate. The engine driving Yellowstone is a geological hotspot, a concentrated plume of anomalously hot material rising directly from deep inside the Earth's mantle. This cross-section schematic shows the process. The mantle plume remains stationary, while the North American plate slowly shifts across it. As the plate moves, the hotspot burns through new crust, leaving a geographic trail of ancient caldera scars stretching across the American Northwest. Yellowstone is not a fixed anomaly. It is the current location where a continuous 17-million-year-old subterranean blowtorch is actively scorching the surface. To monitor this massive system, the Yellowstone Volcano Observatory maintains an extensive network of GPS sensors, satellites, and seismometers. They track every measurable parameter of the park's geology in real time. Currently, scientists see no signs of the deep magma intrusion that would indicate an eruption is building, but the scientists tracking that data are clear about the limitations of our warning window. If an eruption begins to mobilize, the monitoring network would likely give us weeks to months of notice, not years or decades. All of our advanced surveillance ultimately provides an illusion of control. We can watch the system perfectly, but humanity possesses zero technology capable of preventing or mitigating a supereruption once it starts. If the caldera collapses again, the immediate blast releases pyroclastic flows of superheated gas and ash, traveling outward at hundreds of kilometers per hour. Everything within a 100 to 200 kilometer radius of the blast site would be instantly incinerated and destroyed. Then the secondary effects would begin. Prevailing wind patterns would catch the massive, towering ash cloud and carry it eastward across the continent. Thick layers of volcanic ash would rapidly settle over the central United States. This weight would crush agricultural production, poison municipal water supplies, and permanently clog the air intakes of our transportation infrastructure. The immediate physical footprint of a Yellowstone supereruption would essentially erase the American Midwest as a functioning, habitable region. The heavy ash would devastate North America, but the global effects would be driven by lighter gases, specifically sulfur dioxide, injected straight into the stratosphere. This diagram illustrates the high-altitude chemistry. Sulfur dioxide reacts directly with atmospheric water vapor to form a dense layer of sulfuric acid aerosols. That newly formed layer wraps around the planet, acting as a massive atmospheric mirror, actively reflecting incoming sunlight back into space. The result is a volcanic winter. This blockage of solar energy could reduce global average temperatures by several degrees Celsius for years. The historical record confirms this. The 1815 eruption of Mount Tambora in Indonesia ejected approximately 100 cubic kilometers of material, dropping temperatures enough to cause widespread crop failures across Europe, North America, and Asia. A Yellowstone eruption would be 10 times larger than Tambora. A global temperature drop of just 2 to 3 degrees, sustained over several years, would shatter the international agricultural supply chain, producing food shortages that would starve billions of people. By any scientific definition, a Yellowstone supereruption is not imminent. The United States Geological Survey assigns the probability of roughly 1 in 730,000 in any given year. Yellowstone will eventually erupt again. The survival of human civilization depends on our ability to build a society resilient enough to withstand the environmental consequences. Up on the surface, seismometers run, data transmits, and tourists take photographs. But 15 kilometers below, the magma chamber slowly breathes. Underneath it all, the hot spot burns exactly as it has for the last 17 million years, patient, permanent, and indifferent to everything above it. Next episode, Abraham Lincoln, the lawyer from Illinois. He held the United States together through its bloodiest war, abolished the institution of slavery, and was shot in a theater 5 days after the war ended. Our next episode delivers the full, complex story of the man, moving beyond the mythology of the monument.